the next particular aspect here, which is the frequency response. All right. So we have seen this here, that because my transistor has internal capacitances, because I've connected external capacitances here, my amplifier characteristics are in general frequency dependent, and this is voltage gain versus frequency. And if I take, for example, this one is showing you input resistance versus frequency here. Input resistance looking from this side here. Input resistance is also, I should call it input impedance. Input impedance is also a function of frequency here. Obviously, because as I look from here, I'm seeing CE here and CC here and all the transistor capacitances. So you see that effect coming in picture here. So in general, all the amplifiers characteristics are frequency dependent. And when we try to characterize the frequency dependence of an amplifier, we look at this particular picture and we try to find out what is the cutoff frequency here. 3 dB cutoff frequency, which is a lower 3 dB cutoff frequency, and another 3 dB cutoff frequency over here. And that defines the range of frequencies over which my amplifier is frequency independent. And that's the mid-frequency range here. Alright, so we have seen this. External coupling capacitors or bypass capacitors are one source of frequency dependence, and internal transistor capacitances are the other one here. And we also saw in an earlier lecture that low frequency behavior is caused by external capacitances. Typical magnitude may be microfarads. And these ones are caused by internal transistor capacitances. These are much smaller, and their effect becomes important at higher frequencies here. These are in picofarads or even lower values. Okay. And mid frequencies where capacitances can all be ignored here. So a little bit of background before we start calculating the 3 dB frequency here and 3 dB frequency here. This from your EE210 L. Let me very quickly remind you. RC circuit, when I have an R and a C, and we know there are two ways in which we can analyze. We can look at this circuit in the time domain, and we can look at it in the frequency domain. Both of them give us an idea of how fast this particular RC circuit is. Frequency domain, we replace capacitor by 1 by SC here. So all of this, you know, you get the transfer function, and you substitute S equal to j omega. So you get the transfer function in terms of omega here. And so I'm just quickly going over it. So you look at the magnitude of the transfer function, and you look at the phase here, and you plot the magnitude of the transfer function. You see something going like this here. This is the magnitude here. This is the frequency here. But that's not how you typically plot. You do it on a log scale. So you calculate 20 log 10 here. You plot it on a dB scale here. And in a dB scale, you see the transfer function is constant up to a point and then starts decreasing. And you define a quantity called 3 dB frequency here. Frequency at which the gain of your circuit falls by 3 dB here. Okay, which translates into 1 by root 2 of your gain here. Okay. And 3 dB frequency of your RC filter is simply 1 by 2 pi RC. Okay. And this falls at a rate of, all of you know, 20 dB per decade. Okay. So that's the background that we already know. 3 dB is 1 by 2 pi RC here. All right. So once you know 3 dB frequency, you know the entire transfer function, you know the phase, you know all the information about your RC circuit. Okay. So 3 dB includes within it everything that is interesting about the RC circuit here. All right. The other complementary part is the time domain, where you can excite your circuit through a step, let's say, and you know that once you excite it through a step like this here, the output will rise, take some time to rise to its final value, take some time to fall back to its final value here. And so we have concept of rise time and fall time, right? So this rises exponentially, this falls exponentially here. And we have the concept of rise time or fall time, time it takes to go from 10% to 90%, time it takes to go from 90% to 10%. So rise time and fall time, and it's easy to show that these are equal to 2.2 RC, 0.35 by F3 dB. So these are related. F3 dB is also 1 by 2 pi RC, so the two are related together. So if you know 3 dB frequency of your circuit, you also know how long it's going to rise, how long it will take to rise, and how long it will take to fall. The two are related together. Okay. That was a low pass. Low pass meaning R and C here, and it rises and falls. The other simple circuit is high pass filter, which is C and an R, and same thing repeated very quickly. So you get this kind of a behavior. It passes higher frequencies here, rejects the lower frequencies here. Is 3 dB frequency is also the same, 1 by 2 pi RC here, except for the behavior that you see here. Okay. Transient response is similar, except that the previous circuit was a integrator, and this is a differentiator here, so it sort of differentiates. You've learned all of that in 201. So it differentiates, it goes like this here. That's the behavior that you get. And again, you can talk about how long it takes to fall to its steady state value and how long it takes to fall to steady state value. Again, these are related to 3 dB here. All right. These are things that we already know. The most interesting cases are where you don't have a single capacitor or a single resistor. You have multiple, the circuit is much more complicated. The resistive part is complicated and the capacitive part is complicated. Okay. So if you have only one capacitance, then again, the problem is simple. All that you need to do is the rest of the circuit, you convert it, use a Thevenin's equivalent, and you can convert it into one single resistor here and one single capacitor here. So that's sort of straightforward. Multiple resistors, I can have a current source, voltage dependent current source, any kind of a complication here I can handle by converting it using Thevenin's theorem. So we get an equivalent resistance here, and we know that 3 equivalent resistance here will be R1 parallel R2, and we can calculate the 3 dB. So that's sort of straightforward. The trouble comes, of course, so this is a generalization, any linear circuit. All you need to do is find out what is the resistance looking from here, R equivalent, and your 3 dB is 1 by 2 pi R equivalent. Okay? All right. The trouble comes is when I have multiple capacitors. When I have multiple capacitors, then I can't use, in principle, any of those formulas anymore here. These are for single capacitor circuits here. Multiple capacitors, for example, if I'm interested in lower cutoff frequency of an amplifier, lower means lower frequencies, all the external capacitors are important, CB, CE, CC. Internal capacitances I have all open circuited because the frequencies are low, the impedances are very high. So all C pi and C mu that you see here are all very large impedance, and we have ignored them. So now that we have all these three capacitors here, now the general approach for all of this is, in general, what you do is, we are interested in V0 by Vs. This is the transfer function. And we are interested in knowing what is the 3 dB frequency of this particular circuit here. So in general, the procedure is you find out the transfer function. So what you do is you replace each one of them by its impedance or admittance, one by SC, SCB here, one by SCE here, and one by SCC here. And so all of these are there. It's a linear circuit. Do your KVL, KCL, Thevenin, whatever you are comfortable with, arrive at V0 by Vs. So you get a transfer function. And transfer function would be a function of omega. And then what do? You plot it out, and from there you figure out when it's falling by 3 dB, and you get the 3 dB frequency. Okay? Now our interest is not just in getting a number. If we are given all the values, what we are looking for is an expression for 3 dB frequency. And expressions are much more difficult to calculate. Number, I can get it by, plotting it out and figuring out where it is. But an expression is more difficult. But as I said, in principle, you can do it. You can replace each one of them by its impedance and solve it and get it. If you try that, so this is what we are looking for, get a transfer function. And this is a cartoon of it. So it will actually go in a more gradual manner. All right. If you do that, this is what you get for a transfer function. Okay? This was done using a program which automatically calculates the transfer functions of circuits here. So first term is, is in terms of S square, and there's an S cube here, and all these terms are there, CC, RB, RE, RL, and all of that. Complicated expression, okay? The transfer function is complicated. I mean, there are lots of terms in it, okay? Lots of terms in the transfer function. One can simplify it. The circuit, this is a circuit simulator, which we call it as a symbolic circuit simulator, which means that it doesn't act on numerical values, but acts on symbols. And so therefore gives you an expression. And the circuit simulators have become smart also. So if you tell them that I want an expression which is simple, so the simulator will ask, how much approximation are you willing to make? So you say, I'm willing to live with 10% approximation, and you give some typical values of C's and R's. So it simplifies and it gives you this one. All right. So S square and S cube and all of that. So anyway, you have a transfer function, but then again note that it's not, this will have an S is a j omega, and then this is S square and this is S cube. And again, it's a little bit complicated. Extracting 3 dB frequency is more difficult. So what we do is we go to approximate techniques here. And approximate techniques, so obviously we are going to make approximations, and so my the numbers that I will get for 3 dB will not be very accurate. But the goal of our expression is to capture all the important parameters. It's not so much to arrive at a very precise value of 3 dB frequency, but an expression which captures all the important parameters that affect my 3 dB frequency. So that's my larger goal here. So what we do is we determine the impact of each capacitor independently. So the way we find out the lower cutoff frequency is, suppose I make an assumption that my 3 dB frequency is determined by CE, and CB and CC, they don't affect my 3 dB frequency. They don't affect means I can consider CB to be a short, and I can consider CC also to be a short. All right. That's when my CB doesn't affect my 3 dB frequency. Yeah, the signal straight away passes and then gets amplified and appears. So suppose I make the assumption that my CB doesn't matter, it's a short, CC doesn't matter, it's a short, and then I have only one capacitor left. And then I calculate 3 dB frequency, which is determined by this capacitor. Next, what I do is I say, well, this doesn't matter, this doesn't matter, this is the only capacitor which is important. And I determine a 3 dB frequency due to this one. And again, then I determine a 3 dB frequency due to this one. So I'll get 3 different frequencies. Now, if one of the frequency turns out to be much larger than the other, then I say that's the 3 dB frequency of my whole circuit. If they become comparable, then I'm in trouble. Then I'm in trouble. Okay. So our procedure is as follows here. What we do is, it's called the short circuit time constant approach. The idea is as follows. We consider one capacitor at a time, assuming that it plays a dominant role, and short circuit the remaining. Okay. Remember, this procedure is for finding the lower cutoff frequency only. Okay. So we do that. We then determine time constant R equivalent Cj and 3 dB Fj due to that capacitor. Okay. Like this, we determine for each of the capacitors. If one of the 3 dB frequencies is larger by a factor of this 4 or so, is rather arbitrary, depends on how accurate you want to get the value. So if one of the 3 dB frequencies is much larger compared to others, we take this frequency as a 3 dB frequency of the circuit. We are lucky, and that's how it is. Otherwise, we have simplifications. One simplification is you simply sum up the frequencies due to all the capacitors here. Well, this is going to give you highly approximate. There are better approximations which says determine the, I will not go into it, determine the frequency due to each pole and zero and all that. Okay. What we'll do in this particular course is we'll determine due to each capacitor 3 dB. And if one of them is much larger, let's say factor of 4 or 5, we'll take that as a 3 dB. Otherwise, we'll simply sum up and get a better approximation. That's it. Okay. So that's a procedure for calculating the 3 dB frequency of our lower cutoff frequency for our circuit here. Keep in mind that this is, focus on this. There's a big approximate sign here. Sometimes the number that you will get from here will be reasonably close to the actual value. Sometimes it may be fairly far off. But what this expression will do for us is it will tell us the important factors that affect my 3 dB frequency. So that much it will tell, and therefore it's a useful expression. Upper cutoff frequency. Well, upper cutoff frequency, what happens is all the these capacitors that you see here, all of them, the external capacitors, they don't matter. All right, so this we have seen that all the capacitors can be classified into two parts here. Let me, the external and the internal. The internal capacitances are what determines the upper cutoff frequency here. So our procedure is as follows. Note, if you go back and look at the upper cutoff frequency, so we say upper cutoff frequency, what are the capacitors that matter? C pi, C mu, and this substrate capacitance here. These are all internal transistor capacitances. So what we say is, let's say my C pi matters. C pi matters, and C mu and others, they don't play any role. They don't play any role means what? They're open circuit. Remember what we have been doing with internal transistor capacitances? If they don't have an impact on your amplifier, what do we do? They're all open. This is open, this is open, and this is open. So what we do is we say, let's assume that C pi is the one which determines the upper cutoff frequency. And then we open C mu and we open CCS. Then we say, well, let's assume that C mu determines the upper cutoff frequency. And then we open C pi and C mu. Alright, so remember, look at the differences. When we looked at the lower cutoff frequency and we said a capacitor doesn't matter, what did we do? We shorted it. This capacitor, if it doesn't matter, it means it's a short. While in the upper cutoff frequency, if a capacitor does not matter, it's an open circuit. Okay, so that distinction please keep in mind. So open circuit time constant approach is for upper cutoff frequency. So what you do is again, one capacitor at a time, assuming that it plays a dominant role, and open circuit the remaining. Again, determine the time constant due to the capacitor. Do it for each one of those capacitors here. If one of the 3 dB frequencies is smaller by a factor of 4 or so compared to others, we take that as the upper cutoff frequency of the circuit. Otherwise, we approximate upper cutoff frequency by 1 by 2 pi sigma R equivalent Cj. We sum up all the time constants and we calculate the upper cutoff frequency. Again, it's an approximate procedure, and this will give us error, but again, it will capture all the important parameters that affect your upper cutoff frequency. So this is what we call as the open circuit time constant approach, and the previous one was called the short circuit time constant approach. This one gives you the upper cutoff frequency, and the other one gives you the lower cutoff frequency. Okay, let me illustrate that with an example here. Say I have a circuit like this. I have C1, C2, C3, C4, I have a couple of resistors and all that here. The first thing is, when you are given a circuit like this, which capacitor will affect your lower cutoff and which one will affect your upper cutoff? Lower cutoff means what? Remember the diagram, it goes like this here, right? Lower cutoff, the frequency response starts from here, goes up and then goes constant here. So which one will affect? C1, C3. So note the lower cutoff is something like high pass characteristics, and lower cutoff is low pass filter characteristics. Okay, so out of these, C1 and C3 are what determine my lower cutoff frequency. Because note that at lower frequencies, what will happen is C1 will become open circuit and will block V in from going to V0 here. So it affects my lower cutoff frequency. Similarly, note C3 also blocks the signal to going to V0 here. So both C1 and C3 affect my lower cutoff, and C2 and C4 will affect my upper cutoff frequency. So I divide my capacitors into two classes, lower cutoff and high cutoff. And then what I do is, to determine lower cutoff frequency, I'll assume this C2 and C4 to be open circuit. Those that affect my upper cutoff frequency, those capacitors are open circuited here. And so C2 and C4 will open circuit, so we're left with this here. And then we take one at a time. We take capacitor C1 at a time here. If we take C1 at a time, what do we do to the other one? Short it. We short circuit the remaining capacitors here. So we short it, and we now determine the 3 dB frequency only due to this capacitor. And 3 dB, will be the net resistance that this particular capacitor sees. So what will happen is, it will be equal to R1 plus R2 parallel R3 plus R4. R3 and R4 are in series here. R5 is open here. R3 and R4 are in series in parallel with R2, and then this is in series with R1. So we determine the equivalent resistance seen by C1, and that's the time constant due to this one here. Okay, and we determine the frequency due to this. Okay, so we have divided capacitors into two classes, those that affect my upper cutoff, those that affect my lower cutoff. When I look at my lower cutoff, upper cutoff capacitors are all open here, and I'm left with these two capacitors here. Then I take one at a time, considering the other one is short. And so we determine the 3 dB due to C1, and same thing we'll do due to C3 here. We'll get a 3 dB frequency again. So let's skip that. F3 is 1 by 2 pi 3, 1 by this one here. So we get two frequencies here. Now let's take some typical values. Let's put in some numbers here. So I get F1 equal to 95.3, F3 equal to 6.36 here. So obviously F1 is much larger than F3. So my 3 dB frequency will be determined primarily by this one, 95.3 here. So my simple method predicts 95.3, and the accurate, if I do a simulation and determine it, it shows 103.0. So of course it's erroneous, but 95.3 is pretty close to 103. So the approximation works reasonably well because I have one dominant frequency. If on the other hand, let's say this had been 10 or so, and then F1 and F3, what I would have done is sum up. I would have added up F1 and F3, and I would have said that's the frequency. Even now I can add up. If I add 95 and 6, I get 101, which is fairly close to this one. Okay, so if you want to do a more accurate analysis, all you do is determine due to each one of those capacitors and just sum up F1 plus F3. And that's your estimate for 3 dB frequency. Okay. Upper cutoff frequency, what we'll do is these ones will short. C1 and C3 we will short now. And so we'll be left with only C2 and C4. And now upper cutoff frequency, the approach is open circuit. So we'll open circuit C4 and determine the time constant due to C2. Alright, so we have C2 here. I'll skip all that. You determine equivalent resistance, you determine the time constant, and you get a frequency. Then you consider C4, and when you consider C4, the other one is open. So you get another circuit here, and you determine its time constant, and you get its frequency here. Alright, and then if one of them is much smaller than the other, that's the cutoff frequency. And if they're comparable, then you sum up the time constants here. So let me give you an example again here. Let's say F2 comes out to be 0.39, F4 comes out to be 0.2. The two are comparable, right? So one of them is not much smaller than the other. So what I do is I take the 1 by 2 pi sum of the time constants. So I take this time constant and I take this time constant, add them up, and 1 by 2 pi, and I get a value of 0.13 gigahertz. Well, if I do simulation, I get a value of 154 megahertz, which is like 0.15 gigahertz. And the approximate value that I get is 0.13. So note that even though the two are not very far from each other, they are comparable, but the final value that I get is not that bad. 0.13 here, and the actual value is 0.15. Alright, so the method works reasonably well in this particular case here. Okay, even though the two frequencies are reasonably close to each other. So now what you see then is that determining 3 dB frequency boils down to just determining the time constants. All I have to do is take one capacitor at a time and determine the time constant. If I can do that, then I can get the 3 dB frequency of any circuit, any amplifier circuit. All I have to do is repeat these kinds of calculations again and again for different capacitors and obtain the values. In case of upper cutoff frequency, I'll sum up all the time constants. In case of lower cutoff frequency, I'll sum up all the 3 dB frequencies. Not the time constants, but all the 3 dB frequencies. Okay. Alright. So then let's start with the lower cutoff frequency. Now, remember what you'll be doing is calculating the time constant. And time constant is nothing but a capacitor multiplied by a resistor. So effectively what happens is for each capacitor you have to determine what is the resistance that the capacitor sees. Now there are certain resistances which help us in calculating 3 dB here. Look at this particular one. Certain relations which have been derived beforehand and can be very helpful. This tells us, look at this particular one, this tells us that if you take a transistor and there's a resistor connected here in the emitter, collector is ground and all that. By the way, before I proceed with this, remember that all this analysis that I have to do, all the circuits that I'm drawing here, transistor circuits that I'm drawing, these are all, this circuit here, let's go back to the transistor circuit here. This circuit is a small signal circuit. Okay, keep that in mind. All upper cutoff, lower cutoff, all that frequency analysis is all small signal circuit. Okay, it's got nothing to do with DC and all of that. Okay, so it's a small signal circuit. So with that, With that, keep in mind that when I draw a circuit like this and say the resistance looking from here, I'm talking about all resistances which are small signal. And when I draw a transistor like this now, remember the context in which this discussion is taking place. I'm talking about small signal model of a transistor. So this circuit that you see here, these are small signal ground. There's a small signal ground here. And so we say that if you're looking at a transistor with a resistance connected in the emitter, and you ask what is the net resistance looking from here? Net resistance looking from here means between this node and ground. Whenever I draw something like this and say resistance looking from here, it means between that node and ground. Ground is always the reference, okay? So I'll just show you that the resistance looking from here will be equal to R pi plus 1 plus beta R. Okay? Now, where is R pi coming from? You know that between base and emitter, what do you have? If you try to recollect your small signal model, between base and emitter, you have R pi. And then it says, so R pi we can see clearly here. And we know that RE is coming in series. RE is coming in series. But note what happens is, when you look from here, the current that goes into the base is IB, while the current that flows here is IC. So what happens is, this resistor effectively gets multiplied by beta and appears towards the input side. Okay, which we will just see, if you do a circuit analysis. So that's one very useful result. That resistance looking from the base side is R pi plus 1 plus beta R. The other one says resistance looking from the emitter side. When you look into the emitter, again, what does it mean? Between the emitter node and ground. What do you see? You see again R pi, right? R pi here plus RB, but the whole thing gets divided by 1 plus beta. So the resistance looking from the emitter side is R pi plus RB divided by 1 plus beta. That's a very useful result, which we can use it at many places. Third one, resistance looking from the collector. When this is ground and this is ground, the resistance looking is simply R0. Okay, so let me illustrate this. Where am I getting this expression from? All right. So what we are saying is resistance looking from here. So what we do is, you know that if you want to find resistance in your small signal circuit, what you do is you attach a source Vx. There's a current Ix that flows. Vx by Ix will give us this resistance here. We replace the transistor by its hybrid pi model. RC should not be there. It is ground here. So we should put a ground here, and RE is here. Now, all you need to do is solve this circuit to get Vx by Ix. That's all. So if I solve it, Vx by Ix, I get R pi 1 plus beta Re. So any resistance anywhere in the circuit, if you want, all you do is you attach a source Vx, find out what is the current that is coming from that source. Vx by Ix will give you that value. And that's what we find. Resistance looking from here. Note resistance looking from here means between this node and ground is equal to R pi 1 plus beta Re. Okay, which means that when you look from here, R pi of course appears as it is. Anything in the emitter gets multiplied by beta here. And you can see why. There's a current Ix flows here. There's a current which is beta times Ix which will flow here. And the two sum up and flow through this. Okay, so that's why Re gets multiplied by a beta here. So that's a very useful resistance here. Same way now, as I said, using the same procedure, you can show that. If you want a resistance between here, you attach a source Vx, and there will be current Ix going, replace it by hybrid pi model, solve it, you'll get this value. So as simple as that, R pi plus RB 1 by beta. Okay. So these are useful results. Let's come back to our CE amplifier. And we want to calculate the 3 dB frequency. So first thing, we take our amplifier, convert it into small signal equivalent circuit. So VCC becomes ground, and R1 we know comes in parallel with R2. So we write it here. CB is there. To make it general, we have included a source resistance as well. I'm keeping the transistor as it is for a moment. Of course, I have to replace it by hybrid pi model here. RE, CE, RC, CC, CR. Okay. So that's my model or equivalent circuit which I have to use to calculate the 3 dB frequency. I've included all the capacitors that are there, external capacitors. What is the procedure? One capacitor at a time, right? So if I look at this capacitor, I focus on this capacitor, what do I do to the other capacitors? Short it. Short this one and short this one. Okay, so let's do that. We shorted that one and we shorted this one here. What will be the 3 dB frequency? I have to find out the net resistance seen by CB. How much resistance does CB see? Well, to do that, what I ask myself, what is the net impedance looking from here? From this side. What does it mean? Between this node and ground. So the net impedance, so when I look at my circuit and I look right, what do I see? I see R1 parallel R2. What else do I see? Do I see, does everybody note that between here and here, what do I have? R pi. And this R pi is what? Between this node and ground. And therefore it comes in parallel with R1 parallel R2. So the net impedance seen from here is R pi parallel R1 parallel R2. That's the net impedance seen from here. So what will be my 3 dB frequency then? The net impedance seen by CB is RS from this side and R pi parallel R1 parallel R2 on this side, and both of them are in series. Okay? And so that's the net impedance seen by my capacitor CB, and my 3 dB frequency then becomes so much. Okay? So what you are seeing is I don't want to take my transistor, put as hybrid pi model and do that elaborate calculation. I want to use these results here, that the resistance looking from here is R pi, or resistance looking from here is R naught. Use those results to simplify my calculation. Okay. All right. Let's focus on C here. Once I look at that, CB becomes short. This becomes a short. What will be the value now? What is the impedance seen from here? R naught. Okay. Between the collector and emitter, the resistance is R naught. So what happens? Resistance seen from here is R naught parallel RC. And we have been saying that R naught is much larger than RC. So we approximate it by RC here. So what is the net resistance seen is RC plus RL. And 3 dB frequency is 1 by 2 pi CC RC plus RL. That's the 3 dB frequency due to my collector capacitance here, collector coupling capacitance. Alright. Other capacitances are all shorts. Next, this one here. Okay. Alright. So we need to find out now what is the net resistance seen by CE. So how do we do that? Which rule do we use? Go back and see. This is this here. Use this one. Resistance seen from the emitter is what? R pi plus whatever is in the base. They add up and they all get divided by 1 plus beta here. So we use that particular result here. Alright, same thing. Simplify the circuit. RC is in parallel with RL. And this one, does everybody see that? Resistance looking from here will be what? RS parallel, R1 parallel R2. So we replace it by one single resistor. And then, what is the impedance looking from here? R pi plus this resistance divided by beta. Okay? And when I draw like this impedance is where? Between the emitter and ground. Always keep in mind, when I say resistance looking from here, it means between that node and ground. So what we get is, now see, this is the impedance which is R pi plus this RS parallel R1 parallel R2, the whole thing divided by 1 plus beta. And this comes between here and ground, so it comes in parallel with RE. And therefore, my equivalent resistance is RE parallel, this whole thing, that's my equivalent resistance. And my 3 dB frequency is 1 by 2 pi CER. So I've obtained all the 3 dB frequencies due to CE, due to CC here, and due to CB here. Alright, so these are the values here. So let me illustrate it for you, taking an amplifier like this. So we have to do a DC bias point analysis, R pi, GM, AV, everything is given here. If I calculate due to this one, I get 24.4 Hertz. If I calculate due to this one, I get 3.6 Hertz. If I calculate due to CE, I get 2.18 kilohertz. Alright. All the capacitors are same. 10 microfarad, 10 microfarad, 10 microfarad. What will be my cutoff frequency? 2.18. That's the maximum. In this, the highest one determines, okay? The highest one determines the cutoff frequency here. FL will be almost equal to 2.18 kilohertz. Okay. And what does my simulation show? Simulation shows about 2.2 kilohertz. So I get a value of 2.18 and the simulation shows 2 kilohertz. Obviously, we have made some approximations and it's not going to be that accurate, but we have a number which is pretty close. Okay. So procedures then are now is the same procedure for any amplifier circuit. If you want to calculate lower cutoff frequency, is the same procedure that you have to repeat. Take each capacitor at a time, consider the other capacitors as shorts, determine each one of them, and in the end, if one of them is much larger than the other, that's the cutoff frequency. Otherwise, just sum it up. Just sum it up and you get the approximate value. Okay. Now also note now the following thing about your amplifier here. If you look at these FB, FC and FE, it's telling you that which capacitor is the most important one. Which one really determines the 3 dB frequency is this bypass capacitor. If the capacitors are all of the same magnitude, then it is the emitter bypass capacitor which really determines your 3 dB frequency. Okay, so that's the most important one. And therefore, if you want to lower the 3 dB frequency, you're not happy with 2.18, what you have to do is leave this capacitor as it is, leave this capacitor as it is, maybe put a 50 microfarad capacitor here. Alright, so in many of these circuits that you go and see, common emitter amplifier circuit like this, you will often find that the capacitor used in the emitter is much higher as compared to capacitor used in the base and the collector. And the reasons are, you can see here. That has a much more dominant effect on your 3 dB as compared to the other one. And it's very easy to show also. If you start looking at these expressions for FB, FC and FE, right? Look at the three expressions that we have obtained. And if I make some approximations in order to show you, suppose I say RS is negligible, RL is not there, no load is there, then what happens is my FB becomes 1 by 2 pi CB R pi, FC becomes 1 by 2 pi CC into RC here, FE becomes beta by, and just through a couple of manipulations I can show the following. That my emitter frequency due to emitter bypass capacitor is approximately beta times this one. And my emitter bypass, that frequency divided by FC is, the ratio is almost equal to AV. So what it tells us is the following. If the capacitors are of the same magnitude, each capacitor CB, CC and CE are of the same magnitude, FE is going to be 100 times larger than that due to the base coupling capacitor. FE is going to be maybe voltage gain times the collector bypass capacitor. So these are some simple manipulations of these equations to illustrate the fact that emitter bypass capacitor is the capacitor which determines the lower cutoff frequency here. So that's the capacitor to worry about, and that's the capacitor. If you want to make 3 dB cutoff frequency lower, then that's the capacitor that you have to change here. But if you go back and look at the expression here, so if this is of interest to you, one way of lowering FE is by increasing the capacitor. What is the drawback? What's the difference between 1 microfarad capacitor and 100 microfarad capacitor? Apart from the value, what is the difference? 1 will be small and 100 will be a big capacitor. So you can't, the circuit becomes bulky and you have to go to large electrolytic capacitors here. So suppose you don't want to increase CE. How else can you bring FE down? How else can you bring FE down? What will you have to do? I don't want to, use a very, very large bulky capacitor, but I want a very small frequency here. Then I have to look at this term. Now in this term, how do I bring it down? How do I bring this particular term down? Oh, sorry, how do I bring this term? I have to increase this particular term, right? How do I make this term large? Make RE large, right? But RE isn't parallel with this one. So if you simply make RE large, what will happen is this term will become limiting. And which term do you think is important here? if you look at these, well, what could happen is, say if I go back and look at, say I have negligible source resistance for a moment, right? Negligible source resistance here. Then what will happen is RS is negligible, and so this term is negligible, and I'm left with R pi by beta. What does R pi depend on? Collector current. Now how do I make R pi large? How do I make R pi large? Reduce the collector current. Now will something else get affected if I reduce collector current? Gain depends on IC times RC divided by VT. So what happens is, as you try to make R pi large by reducing the collector current, what will happen is your gain will start dropping. And now you are seeing the well-known relationship that you might have read about, that I have a trade-off between gain and bandwidth. As I try to improve my bandwidth, as I try to improve my frequency response, something else will suffer. My gain is going to go down if I start addressing R pi. Now similarly, you can go ahead and look at what if you increase RE. Say this is not the limitation. Say R pi is still very large. RE is the limitation here. What will happen then? Make RE large. What will happen due to RE large? If I make RE large, what will happen to your circuit? If you make RE large and you don't touch collector current, right? Collector current is as it is. Then what will happen? This drop will increase. And what will be the effect of increased VE? The swing is going to decrease here. So what you're seeing here is everything is coupled to everything else here. The gain is coupled to input resistance. Input resistance is, the gain is coupled to output resistance. The gain is, or the swing is coupled to lower cutoff frequency. These are all connected together. All right. So we have a handful of components here. We have RE, we have RC, we have R1, R2, and they affect everything. They affect my gain, input, output resistance, voltage swing, lower cutoff, upper cutoff. And obviously, what happens is you try to improve one quantity, something else will suffer. Okay, and that's what you will find here. That's what we are finding at this point here. Okay. So whether you increase RE or whether you increase R pi, that's going to affect your the remaining parameters that you have. Okay. All right.